This week we're going to discuss the fundamental theorem of calculus. Now, the fundamental theorem of calculus, well, first, it's called fundamental for a reason, and we'll discuss that a little when we get into these remarks. But it is a very nice result in calculus because it ties together in a couple different ways how the derivative and the integral relate. Fundamental theorem of calculus has two parts. This video will be on part 1, the next one will be on part 2, as the title suggests. So let's talk about it. Well, let's state it and then talk about it. Let f be continuous on a to b, closed interval a to b. Part 1. If capital F of x equals the definite integral from a, so from some value, to x of f of t dt. Now the t here is just because x is used to define the function. So all of the integrals we've seen have been, with an x here, f of x dx. But x is the independent variable for this capital F function. And notice here our independent variable is the upper bound of the integral. More on that in a moment. But capital F of x is defined to be the integral from some number to x of the continuous function f, and here we're just going to use t because x is already used. We're defining capital F to be that function. This function gives an area. Remember, the definite integral gives an area. More on that in a moment. But capital F is defined to be that function. Then f prime, capital F prime, equals lowercase f of x on this interval a to b, the interval on which the function is continuous. So right there we have a result. If capital F is defined to be this function that gives us an area, then its derivative is this inside function of x. And in our computations we'll see more what happens if it's not just an x. But if it is just an x, its derivative is the inside function. That's one result. The second result for part 1 is this capital F is continuous. Again, more on that in a moment. In our discussion of the first part, I'll mention a little about what that means. Part 2, the definite integral from a to b, f is continuous on the closed interval a to b, definite integral from a to b of f of x with respect to x. Here we didn't already use x, so we can use x, equals capital F of b. This is not the same capital F as is up here, because it is a different part. This is part 2. Equals capital F of b minus capital F of a, where capital F is any antiderivative of f. So last week, remember, we had the indefinite integral and the definite integral. The indefinite integral gave a family of antiderivatives. The definite integral gave an area. And they had similar notation. The only difference was the definite integral had bounds. But there was no reason last week to believe that those two concepts should have such similar notation and terminology. But this part, part 2, provides a nice justification for that, because right here we have a definite integral. And to compute that definite integral, all we need is an antiderivative of lowercase f, of the integrand. So here, part 2 says we can use an antiderivative to compute a definite integral. And it relates the indefinite integral and the definite integral. Well, it relates the antiderivative and the definite integral, and the antiderivative is related to the indefinite integral. So we have 3 remarks. I probably alluded to a couple of them. Yeah, I alluded to the third remark. But 2 remarks on part 1. Part 1 relates the derivative and the integral. In particular, it says the derivative with respect to x of this definite integral in a way cancels out. First part says the derivative The conclusion for the first part, then capital F prime, well, capital F prime is the derivative of this integral. In a way, they cancel out. More on that in our computations for this video. Another important result, all three of these remarks provide reasons that this is such a fundamental theorem of calculus. This one could be argued is the most important consequence of the first part. Could be argued this one is. But we have indefinite integrals which give antiderivative rules. But that list was much shorter than our derivative rules. And consequently, it's not clear with just those rules that every function has an antiderivative. For example, there's no rule for tangent. Is it clear that tangent has an antiderivative? Well, if you looked at worksheet, I'm going to get the week wrong. It was problem, I believe, 1B of the chain rule worksheet, which would have been, let's see, that was the week after the first test. That was week 6. I believe problem 1B in week 6 actually showed us a function whose derivative was tangent. But just with those rules, it is not clear that tangent has an antiderivative. Part 1 guarantees that tangent function and any continuous function does have an antiderivative. Lowercase f has antiderivative here, capital F. Part 1 guarantees that any function, any continuous function at least, has an antiderivative. Tangent's not continuous everywhere. You can close down the interval so that it is continuous on that interval. A very important result of the fundamental theorem of calculus. Something like cosecant. The derivative of cosecant is negative cosecant cotangent. What's the integral of cosecant? What's an antiderivative of cosecant? That actually turns out to be a pretty complicated Calc 2 integral. Third remark, part 2, I alluded to this. Part 2 says, but remember, the definite integral is defined as a limit. It's defined using the limit as n goes to infinity of the approximation using n rectangles. But part 2 says, if you can find an antiderivative of the integrand, then the limit definition is not necessary for computing a definite integral. I believe I did not define integrand last week. I probably should have. Integrand, I-N-T-E-G-R-A-N-D. That's this thing in here, lowercase f of x. Maybe I shouldn't underline that since it shouldn't be underlined in the statement. The integrand is what's between the integral sign and the dx. But if we want to compute a definite integral, all we need is an antiderivative. Any, more on that in the next video. But let's look at a visual for the first part of the fundamental theorem of calculus. And I'll discuss a little more about what it means for the function to be, for this capital F to be continuous. And I have a visual for that I like to use. And it actually helps, in my opinion, it helps understand a lot of Calc 2 and Calc 3 integrals that you have to do. In Calc 2 and Calc 3, you'll use integrals to find areas and volumes. Actually, today we're going to find some areas in the next video. And in Calc 3, you do a bunch more integrals, much more complicated integrals with extra variables. And this visual that I have here helps me figure those out. What does this mean? Well, capital F. What's capital F? Let's take a lowercase f. Let's call this lowercase f. Continuous on A to B. There's A, there's B. It's continuous. I'm going to block those off because capital F is a function of x. What's x? Well, x could be anything. For this diagram, I'm going to assume it's between A and B. Let's say it's here. What does capital F give? Capital F of x gives the definite integral from a to x of this function gives, I'll just say that, area. Capital F gives that area where x can go, we'll just say from here over to B. It gives that area. Now, what does it mean for this function? That was a car driving by, in case the microphone caught that. What does it mean for this function to be continuous? Well, in Calc 1, when we discuss continuity, we aren't entirely honest. Well, I wasn't entirely honest. But it's standard to not be entirely honest when we discuss continuity, because the definition of continuous function looks like that. That says when. And this is just an absolute value and an extra line. So we say in Calc 1 the definition of a continuous function is you can draw it without lifting your pencil. What does that mean with an area? Well, it doesn't really mean much for this capital F, because capital F, while it does give you a number, capital F of x does evaluate to a number. This area is a number. But it's not clear how you can draw that function as x varies. You don't need to know this definition. I'm going to erase it because I don't even like looking at it. But what does it mean? Well, the way I like to see it is we can view this area. So remember, the definite integral is defined with rectangles. We can view this area between A and B as being filled in by infinitely narrow rectangles. Infinitely narrow rectangles would look like lines. But we can understand this area being filled in with infinitely narrow rectangles as this x value varies between A and B. So this type of visual can help set up many integrals in Calc 2 and Calc 3. But I always like to view the integral as taking a line like this and filling in the area, and this line can go anywhere between A and B, and it drags along this area with it. And what does it mean for it to be continuous? Well, that gets into what I said about infinitely narrow. But I like to say this area gets filled in by these lines in a continuous way. I think that visual is, it's an informal visual, but I think it's a useful visual. So let's look at some examples of computations we can do using the first part of the fundamental theorem of calculus. Let's do these four examples. Find capital F prime of x. So the first part of the fundamental theorem of calculus said we can find the derivative of a definite integral. Find capital F prime of x. Here we have four examples. First, capital F of x equals integral from 1 to x of 1 over t cubed plus 1 dt. So you could, if you could, evaluate this using the second part of the fundamental theorem of calculus, if you could find an antiderivative of that function. Very complicated. That's among the more complicated you could be asked in Calc 2, this actual integral. But here we can find the derivative of this using the first part of the fundamental theorem of calculus. I'll just say we use fundamental theorem of calculus part 1 directly, which says f prime of x is this integrand when you have the bounds starting at a number and the upper bound is an x. The derivative of this integral is just this inside function of x. So here, capital F prime, replace t with x, equals 1 over x cubed plus 1. Part B. So first, we have here integral from 4 to x cubed of cosine of t dt. Now, we technically could, the derivative of sine is cosine, so we could use that here. I'm going to use the first part of the fundamental theorem of calculus. But notice here Well, notice the lower bound is a number. The upper bound is x cubed. The first part of fundamental theorem of calculus applies only when the upper bound is just x. Where have we seen a reduction of a derivative computation to a single variable? Well, let's let u equal x cubed. Then, let's see, where am I going to write this? Well, okay. Then, f is now a function of u. What's f of u? Integral from 4 to u. Oh no, this one was the cosine one. Of still cosine of t dt. Replace all u's, or replace all x cubes with u. Now f is a function of u. We can find the derivative of f with respect to u using the first part of fundamental theorem of calculus. I'm going to do that over here. So I'll say by first part fundamental theorem of calculus. Here I'm going to use the fractional notation for the derivative because I like the chain rule like that. F prime of x df dx. I'll write that down here. But by the first part of fundamental theorem of calculus, df du, the lower bound is a number. It doesn't have to be a 1. It could be a 4. As long as the function is continuous starting at that point. By the first part, df du is cosine of u. What's du dx? Well, it's 3x squared. So, df dx, which equals f prime of x, equals df du du dx. df du is cosine of u. du dx, well, it's x cubed, so du dx is 3x squared. We can get rid of u from our answer. So this equals 3x squared cosine of x cubed. So here we used our chain rule substitution, the u substitution, to find this derivative. We're still finding a derivative. The chain rule still applies. And if you can apply it, it still applies. So let's do these next two. But before we do those next two, when we were doing chain rule, we saw that there was a way to arrive at the answer without necessarily going through the substitution. So I'd like you to compare that answer to the original function. Which I guess I could have left here if I just, whatever. I already erased it. So what was the original function? The original function, integral for x cubed cosine t dt, there's a d. So here, the first part of the fundamental theorem of calculus, as we saw in part A, and as we saw in the after the u substitution, resulted in substituting that in for t. So we can do that here. Notice we do have that here. But also, if that is more than just an x, you would apply chain rule by multiplying by its derivative. So just like with derivatives, if we have more, just like with standard chain rule questions, if we have more than just an x up there, we can still take the derivative normally by making that substitution in this case, but then by multiplying by its derivative using the chain rule. And the u substitution does show that. So for these next two, I'm not going to write out the u substitution, but you certainly are welcome to. Part C. F of x equals what? Integral from root x to 2 of t plus 1 over log t with respect to t. So the first observation is the first part of the fundamental theorem of calculus doesn't apply to this yet. Why does it not apply? Well, the first part, we need the lower bound to be a number. We need the upper bound to be a variable, or a function of x, less specifically. We don't have that here. The lower bound is a function of x. The upper bound is a number. But we can use a definite integral property to flip that around. What happens if you flip this around? Well, those aren't equal. What happens if you flip that around? Property 2 of definite integrals says the cost of flipping the bounds around is a negative. And because negatives will just carry through in the derivative, we can now take the derivative of this function, of this integral, using the first part of fundamental theorem of calculus, and then carrying the negative. Up there we have a function with more than just an x. We have a root x. So you could do u equals root x and follow as in part b. I'll just say the answer. F prime of x is negative. Replace all t's with root x plus 1 over log root x. Don't worry about simplifying, with the x to the 1/2 coming out, or the 1/2 coming out. But that's not it. That would apply if that were just an x and we replace t's with x. But that's a root x, so we need to multiply by the derivative of root x. And I'm just going to write this as one function equals negative and you can leave your answer. I am actually going to pull the 1/2 out of that because it looks better if I do. If you left your answer like this, that would have been fine. That's perfectly fine. Here, the half from that comes out front, and the half and the 2 will cancel. But we had the derivative. We used the first part of fundamental theorem of calculus and the chain rule to find that derivative. So now let's look at part D. And I think I'm going to need the entire board for this. Well, maybe I won't. D. Integral from, maybe I should write capital F, f of x equals integral from x cubed to x to the 4th of 1 over t cubed plus 1 dt. So how are we going to do this? Well, part C we couldn't apply fundamental theorem directly. We had to be clever before we could apply fundamental theorem. Here, we also can't apply it directly because we need a number on the bottom and a function of x to be on the top. We don't have that. We have functions of x on both spots. Well, what can we do? Well, we have another property of definite integrals, property 5 from last week, which says you can split a definite integral. Well, it says the definite integral gives this area. You can split that into 2 pieces, which would split it into 2 integrals. So let's do that. We need somewhere between x cubed and x to the 4th. Well, let's just throw a number there. Integral from x cubed to, how about 5? That's a number. Does that work? Well, let's see. It will work if the function is continuous at that number. So here, any number would work except -1. In this case, you would not be able to split it at -1. Why? Because f of t is not defined at -1. You get a 0 on the bottom. So we can do it at 5. We could have done this one at 0 or 1. I chose 5 because, I don't know. No reason. Maybe there was a reason, I don't know. But now we have two integrals. This first one, meaning the second one, we could compute using the first part and a u substitution. But this first one looks like part C, so we're going to have to flip it around first so that the first part of the fundamental integral calculus applies. So what does this equal? Well, negative integral from 5 to x cubed, 1 over t cubed plus 1, and then plus the integral from 5 up to x to the 4th, 1 over t cubed plus 1. So now, capital F is two things added together. We can find the derivative one piece at a time. So I'll just say, so f prime of x equals, maybe I'll make the equal signs line up because that looks nicer, equals what? Take x cubed. So you could, again, let u equal x cubed here, let u equal x to the 4th here, and follow as we did in B. I'm going to do that in one step. What do we get here? Well, replace all t's with x cubed. So you get x to the 9th plus 1 in the bottom. What do you get in top? A negative and a 3x squared. Over here, what do we get? Well, replace all t's with x to the 4th. X to the 4th, you have 3x to the 4ths next to each other. That gives you 12 total x's. And we have a 1 on top, multiplied by the derivative of x to the 4th, 4x cubed. And you don't have to worry about, combining on all that. You have better things to do than that. So the first part of fundamental integral calculus, the computations would look like this. But the remarks at the beginning of the video are definitely very important for understanding what it's actually saying. Computations for them, we are going to be finding derivatives of definite integrals. And on the worksheet, the first two, I believe it's the first two, in part B, you could have done that without the first part of the fundamental theorem of calculus by evaluating this definite integral using the fundamental theorem of calculus part 2. It would equal, well, we haven't had that video yet, so after the next video you might want to come back to what I'm about to say. This would equal sine of t evaluated at that minus evaluated at that. So sine of x cubed minus sine of 4, and then take the derivative of that. The first one of these, and I think the second one on the worksheet, you can do without the first part of the fundamental theorem of calculus, meaning you can evaluate the integral and then take its derivative. But the first part of the fundamental theorem of calculus says you don't have to do those two steps. You can do it in one step. But do try the first two fundamental theorem of calculus part 1 questions both ways.